Hello, everyone, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Riddell, and I will be your host this evening, afternoon, or morning, depending on which time zone that you live in. As you all may know, our goal is to have Python thrive within the National Lab system and associated research sites. In support of that goal, we are joined today by guest panelist Todd Gamblin, who leads the Packaging Technologies Project in the U.S. Exascale Computing Project as part of, or in addition to LLNL's DevRamp project, lots of projects that Todd leads on developer productivity, and he is also part of the LLNL Strategic Initiative on Software Integration. But before we get into the agenda and introduce all of our panelists today, I want to remind everyone of a few key points about these exchanges. This call will be recorded, edited, and posted online. As a consequence, please be conscious of the information in the questions that you may ask to ensure that you're not accidentally sharing anything that is privileged or requires clearance. Additionally, as you all know, we are a growing community, and we would like to stay in touch with each of you. If you would like to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on our website, meetup.doepy.org. You can additionally find recordings of all of our past exchanges on this site as well, and even a recording of today's exchange once we've had time to process it. For those of you who have never joined us for an exchange, I would like to share with you that we typically break these events down into 4 parts. First, we'll introduce our fantastic lineup of hosts and guest panelists so that you may all get to know them as well as their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about best practices in software development and where they fit into the world of academic and scientific research. Third, we will turn things over to our guest panelist, Todd, who will share some prepared remarks on Python as well as his work and how he's using it to make the lives of scientific researchers easier. And then to wrap up, we'll have a full discussion about the points brought up by Todd. And for everyone joining us in the audience, this is your chance to ask questions and engage with our panel to help us all understand where Python fits into the life of a researcher. Of course, this is our website where you can find all of our materials and past recordings that I shared with you. Just wanted to make sure that you all had it here, meetup.doepy.org. For our host panelists, I will start by introducing myself more formally. Hello everyone, my name is Cameron Riddell, and while I'm not affiliated with a specific research lab, I do have a background in academic research as I studied cognitive sciences in graduate school. For today's exchange, I would love to discuss any and all questions related to just general computing in Python or specific concepts that as part of Python's vast scientific computing ecosystem related to tools such as NumPy, Pandas, and Matplotlib. Next up, we are also joined by James Powell. James, I noticed that you're not affiliated with a research site either. Can you tell us a little bit about yourself and what types of questions you would like to hear today?
Hi, everybody. I serve as the chairman of the NumFocus Board of Directors, where NumFocus is the 501c3 nonprofit that fiscally sponsors many of the tools that we use every day. And so one thing I would love to talk to all of you about is how do I give back to the community? How do I become more involved, not just in scientific computing in my small niche, but in scientific computing as a global movement using tools like NumPy, Pandas, SciPy, scikit-learn, Jupyter Notebooks, even the Julia language.
Fantastic. Thank you so much, James. Looking forward to discussing a lot of these questions as part of our game, as well as some of Todd's work with you. Next up, we have Thomas Caswell. Tom, you work at the Brookhaven National Laboratory. What is it that you do there, and what types of questions are you here to answer for us today?
Hi, my name is Thomas Caswell. As Cameron said, I'm at Brookhaven National Lab, where I work in the Data Science and System Integrations group. In that role, I help build data acquisition, management, and analysis software to support the synchrotron. I'm also the project lead of Matplotlib, and I'm happy to discuss anything about Matplotlib, H5Py, or generally how you go about designing libraries for use by scientists.
Fantastic. I think we'll have a great high-level discussion about packaging and software management with this group. But I also want to introduce Tanny Chavez. Tanny, I noticed that you work at Lawrence Berkeley National Laboratory. What is it that you do there, and what types of questions are you here to answer for us today?
Hello, yes, I am a computational research scientist at Lawrence Berkeley National Laboratory, and I mostly work on the development of machine learning algorithms or AI technology, but more so than just developing the algorithm is also focusing on how to make these tools accessible to a larger scientific community. So those are the type of questions that I would love to hear more about. Regarding on how to create these specific AI or ML tools and how to share them with the larger community.
Perfect. Very happy to have you here, Tanny. And moving on to our guest panelist, drum roll, Todd Gamblin. Todd, you work at Lawrence Livermore National Laboratory. Tell us a little bit about what you do there and what types of questions you would love to hear from the audience today.
So I lead the Spack team, which is the project I'm going to be talking about today. That's a package manager for HPC, so I won't talk too much about that. I work in the area of sort of cloud HPC convergence and how we could better use cloud resources for HPC. So I'm fine for questions about that. And then also I'm just in general into open source and software sustainability for HPC and scientific software. So happy to talk about that too.
Perfect. I think we're going to have an absolutely fantastic discussion. I can't wait to get to your prepared remarks. But I do want to announce that anyone can become a host panelist. All you need to do is reach out to us. Our email will be posted in the chat by my colleague, Daniel Brown. So Daniel, if you could post our email in the chat, our DOEPy email, I would very much appreciate that because I want to get to know more of our audience and I want to interact with more of you and invite you to come up on stage and share your thoughts about how you use Python and interact with our guest panelists. But I would now like to move on to our game that we have prepared for you all. Now, our game is on a little bit different of a take. It's a coding activity. I should specify that. Our coding activity is a little bit different than the ones that we've done in the past. This is going to be more high level. We're going to be talking about the do's and don'ts, not just the do's and don'ts, but the when and when not. I would also like to share that we have been joined by one more host panelist, Jan. And Jan, if you are with us, I would love to hear a little bit about what you do and what types of questions you're here to answer for us.
Yeah, sorry for being late. Yes, my name is Jan. I work at the Los Alamos National Lab on the interface between computational science and material science. So I develop a lot of software for the material science domain and also work a lot with a Conda Forge package manager to distribute the software and make it very easy for people to install the first version and get started with the software package. So I guess in total there are now like 500 packages that I maintain, and we're getting close to reaching 100 million downloads for those 500 packages. So the materials community is finally moving on and using the Conda Forge ecosystem quite a lot.
Yeah, that's absolutely fantastic. I know with a lot of these types of projects, right, making sure that your environment is reproducible and that all you need to do is run one line to get everything you need set up is just absolutely fantastic. All right. And I would like to invite James. James, you'll be sharing our coding activity for the day. What have you prepared for us specifically?
So this month's coding activity is called, Are You Sure You Need? The point of this month's coding activity is to try to answer the questions for our colleagues who read about something brand new, a new tool, a new technique, a new feature, and they are convinced they need it, but you kind of want to guide them towards really understanding, are you sure you need something instead of something else? Let's take a look at the rules. The rules are very simple. We'll present you with 5 rounds where we'll ask a question or we'll present something that a scientist might come up with. I'm pretty sure I need this. And our panelists will be invited to try to guide the hypothetical scientist or the hypothetical researcher to the right conclusion by asking them questions. Are you sure you need such and such instead of such and such? Are you sure you really need to write all of your code in assembly because, C++ might be a little bit easier. Are you sure you need to write your code in C++? Because maybe Python might be a little bit easier. And to see if we can help guide them and to share with each other the questions that we ask ourselves in making a proper determination for when do we actually need some advanced approach. And so why don't we get started with the very first round? This round is, are you sure you need a web UI? The scientist comes to you and says, I need to learn JavaScript, I need to learn React, I need to write a React app to connect to some data, maybe it's stored in a tool like Tiled, and you want to ask them, are you sure you need that? Or maybe we could just host a Jupyter notebook with voila. Panelists, what kind of questions would you guide the scientist to asking themselves to guide them to maybe not necessarily writing a fully fledged TypeScript-based React app to display their data?
How much interactivity do you need?
Very good. So if they don't need a lot of interactivity, maybe just a Jupyter notebook with some IPy widgets is good enough.
Or maybe just a statically generated website with some safe plots is enough.
Absolutely. Other thoughts? Okay.
Maybe also, what is your audience? So is it just an internal tool, or is it a tool that you want to make accessible to the whole world? Again, I would use different kind of levels of quality or like stability of the solution, right? So for internal tools, we use Voila quite a lot. External, I'm not yet so sure if we really want to have Voila facing externally.
And Jan, I think there's a subset of this question, which is web UI versus typical PyQt or tkinter style native UI
like
as well.
What is very beneficial for us is really to have like a shared Jupyter environment, right? So something like my binder internally where people can just interact with it, and I can share the link. People can interact with the data, but basically interact with it in a small Docker environment where they don't have a lot of resources, but enough resources to quickly access the data and work with the data on a small way.
Now, Cameron, there's one more step between the fully fledged, completely custom UI and just a Jupyter notebook that's hosted. You have tools like Dash and Panel and Mill. How would you try and get somebody to really narrow themselves to looking at maybe that middle ground? Cameron?
When examining that middle ground, I would definitely ask, how much time do you have to learn a new technology? If they don't have the upfront time or the bandwidth to really take on learning something like React or even learning the really detailed, in-depth version of JavaScript, then that's when I would probably orient them towards just use something. If you know Python already, right, getting something up and running in Panel or Plotly Dash is quite straightforward. Now, you will eventually hit a wall of what you can and can't do with those tools, where if you had learned JavaScript and React from the start, you wouldn't be hitting that wall. But there's that upfront cost that you have to pay for learning a new technology. So that's when I would try to orient them towards something like that. And you only really need something like Panel or Plotly Dash if you've already tried something as simple as Voila, or you don't want to use the notebook environment at all, and you've already hit the wall of what that can do. So you kind of have these tiers of flexibility that you gain, but with more flexibility comes more complex tools that you need to understand and learn in order to really leverage their power.
So Cameron, when they come to you and say, I need a React JavaScript UI, you say, do you really need to spend the next 3 months learning how to write JavaScript and how to write React? Fantastic. Let's take a look at our next round. The scientist comes to you and they say, I really need the cutting edge AI/ML techniques. Can you please help me install TensorFlow or PyTorch or something even more esoteric in order to analyze my data? And you look at them and you say, are you really sure you need AI/ML techniques? Maybe just simple statistical methods or linear regression is good enough? How would we help guide them towards the right answer?
I think I would probably say that it is good. I think most of us at some point will probably just jump into trying to analyze this data without probably taking a deeper look at it before trying to see like certain correlation or like even feeding a linear regression. just how about we just stop before doing that? We just take a little look at the data. I'll probably say, have you taken a look at the data? How does it look like? How big is it? Do you need to do some dimension reduction? How would you like to prepare your data set before even jumping into analyzing it? And also, what is the purpose of analyzing the data? What are we trying to find? What is our ultimate goal? Maybe we're just like taking a deeper look at the data before even analyzing it. It might give us some clues on how we should tackle this problem.
So the question is, are you sure you need to go buy $20,000 worth of GPUs? Have you looked at the data yet? Other thoughts?
I think one of the strong advantages, especially within the academic realm, of more traditional types of approaches to statistics is that it requires you to have a reason to go searching. A lot of the AI ML will kind of examine some of the data for you and say, oh, here's something significant or here's something cool. But I think a lot of research is done. You need to have lines of reasonings for your questions. You need to have done research in order to figure out what are you looking for when you collected this data in the first place? What was the question you were trying to answer? And applying simple or more fundamental statistics is a great way of avoiding the whole fishing trip kind of experience of performing experiments or organizing your experiments with a specific question in mind that you want to try and answer.
So as we move into our next round, one note is sometimes they do need this, and sometimes we need to just find the right questions to really triangulate what it is that our end users need. And so in our next round, the researcher comes to you and they say, I need some time on a supercomputer to analyze my data. I need to do all of this out of core. I've heard exascale is a big thing, and it's certainly a very fancy name. Are you sure you need exascale computing? Maybe simpler approaches using commodity computing clusters, approaches like Dask might be good enough. And I would love to hear from somebody who works on an exascale project and also somebody who doesn't. Maybe I'd love to hear from Todd how he helps guide his users to when they really do need the supercomputer or not. And I'd love to hear from Tom as well.
Sure. So I do work at Lawrence Livermore, where we have a gigantic HPC center. So to some extent, most of our users need a gigantic supercomputer. But we do have a lot of folks who are working on smaller projects. I think whether you need a supercomputer to analyze your data really requires a lot of pre-analysis to figure out if, just how many computational resources do I need to analyze the data, right? I think most of the folks who do run on the big machines understand that pretty well for different problem sizes. How many compute resources they need, how much I/O they need, and so on. But there's a lot of sizing up that needs to be done beforehand. So I'd say if they're just jumping to maybe if I ran this on a supercomputer it would go faster, I'd back up and do some analysis first, just back of the envelope stuff.
And I'd absolutely love to hear from Tom. I know you have a lot of users who are interested in Dask, but at what point do you really try and triangulate? Maybe is Dask not enough? Do they actually need exascale?
So I would ask, is it really compute bound or I/O bound? At least in the synchrotron space, we have a lot of users who generate extremely large volumes of experimental data, but then load it up, look at the image once, and then throw it away. And something like that, I don't think you're really able to leverage everything a supercomputer can give you. Ask questions: is your algorithm amenable to something like MPI, and the amount of parallelism that you can get out of that, or is it really a pleasantly parallel problem where you can easily chop it up into little pieces and just let individual workers run it without much cross communication?
And also, if you're talking about exascale, that you need to ask them they can even run on a GPU, because a lot of these folks don't have algorithms that are written to run on the GPU, and so if they can't take advantage of that, they're throwing out 98% of the performance on the machine.
So the question is, are you really making use of what you already have available to you before you even reach for something like a supercomputer?
Well, I would say, in particular, in the computing, high-performance computing part, to be prepared for it, I would always recommend to start with something like MPI for Pi. Right? So also MPI, like migrating from something like multiprocessing to MPI for Pi is no longer such a big step. They have the ability to spawn individual tasks, so I can do the trivial parallelization also on an MPI level. And once I have this, I have the ability to scale beyond just a single node in a similar way that Dusk can do it, but already being conformant with the requirements that a supercomputer might have. So on our side, a lot of the workflows are now trivially parallel, so they do the same computations on different kind of atomistic structures. And I always try to motivate people to already make this in a way that it's working with MPI for Pi, to be able to scale it out when they need it.
That is a great segue to our next round. Jan, the scientist, comes to you and said, I've heard about this thing called Rust. I really need to learn it. It is very hyped up. And you think to yourself, are you sure you really need something like Rust? Maybe you do, maybe you don't. But there's also other options. There's Numba, there's Python, and there's other approaches. How do you guide them to really understanding and triangulating? Do they really need Rust? Do they really need some of these fancy low-level tools? Heaven forbid they ask for Zig next.
So yeah, I guess the question is again, like, what is your use case and where do you want to invest your time, right? So like, if it's really, you need the security of your code, then I would say, okay, go for Rust. But everything else, maybe C or even Python would be fine, right? And particularly for my applications, commonly we have the high-performance simulation codes still written in Fortran or C, but then the challenge is more on top of them, how do we coordinate huge workflows of these codes and how we aggregate the simulation data, the result of multiple of these calculations.
Tanny, there's kind of a tension in these kind of questions because a lot of the tools that we use for data analysis, they hit a brick wall and you just can't make them faster. Pandas has a couple of these brick walls in it specifically. And then you want to reach for another tool that you might write in Rust or something that you might write from scratch, but then you got to rewrite everything that they provide you. How do you help your AI/ML users really figure out, is it worth the effort of rebuilding everything that I get more or less for free from some of these frameworks in order to get that speed, or maybe trying to find some middle ground or some accommodation with the inherent slowness of some of the tools?
Yeah, I think that overall, there is usually like a discussion attached to this, of course, in the sense of, what is like the main goal, also what is, I would like to call that kind of like the latency, like what is the amount of latency that is acceptable for their analysis. Is this like analysis that will run on the fly or not? And whether or not there are already some tools that might be already accessible in the same framework where this application is already running. So I think that overall, before jumping into either a new coding framework or new technology in general, we would like to first figure out what is accessible that we probably wouldn't know about before moving forward and committing to changing big parts of our project. Also taking in consideration what is our timeline and what will be the expectations at the short term. So I think those are the things that we usually keep in mind.
You'll lose a lot of time reconstituting all the things that you get for free from those frameworks. And if you have that time, you can spend it, but do you really have the time to spend 6 months rebuilding all of that from scratch, or do you need to deliver very quickly? Fantastic. And that brings us to our, go ahead if there's one more comment.
I'd also ask, have you profiled your code and know where it's slow?
And the sad thing is if they say, well, I haven't even profiled it, I'm not even sure if it's slow, you might say, well, hold on a second. Maybe what you already have there is about as fast as it's going to get. Fantastic. And that brings us to our final round. This is ripped from the headlines, an actual thing that somebody said to Cameron just the other day. I need a library to replace Matplotlib. Matplotlib is not good enough for my publication quality graphs. I need to rewrite it from scratch. And the question is, are you sure you need custom code? Are you sure you need to rebuild these things from scratch as opposed to, not?
I think one of the things that you realize quickly when you try to write an abstraction layer over some lower level tool is you quickly realize you don't know how to use the lower level tool in the first place. So if you think you need to write a library to replace something low level, I would ask, do you know how to use that low level tool? Because if you did and you knew how to use it well, you might feel less of a need to rewrite it because you actually get it.
Cameron, I see this a lot when people say, oh, I'm so frustrated with pandas. Let me write my own replacement to pandas. And my answer is, well, oftentimes what you would end up writing is probably going to look very similar to how pandas is already. You're just going to spend a lot of time spinning your wheels, coming back to the same conclusion of what we already have. Todd, do you have a comment on rewriting open source tools?
I would ask, what assumptions are the existing tools making that you don't want to make?
Very good.
I love that, Tom.
How do they identify what those assumptions might be? For example, does matplotlib give an enumerated list of these are the assumptions we make? Otherwise, go figure it out yourself?
I don't think we have that enumerated list, but I think this goes back to Cameron's point of if you have that discussion, then you could work through what they think your projects are assuming and help work through if that's actually true or not, and if there's a way to extend the existing libraries in a way that serves their needs that isn't a wholesale rewrite. I feel like I cut Todd off. I'm sorry.
Oh no, that's fine. I would be pretty skeptical of a wholesale rewrite of anything of the scale of pandas, NumPy, or matplotlib, because those are huge libraries that lots of effort has gone into. So I'd ask them what they mean by rewrite.
And Todd,
I suspect they are just thinking of rewriting a very small portion of the thing, and maybe that's fine if they just want to rewrite something to do like one plot. But I don't know if they want to create a library like that. Those weren't built by single people; those were built by communities. So I don't think they can replace that effort.
Any comments on the experience that some of the physicists at your facility have had with very custom tools like Yorick, which are maybe maintained by a single person and pull people in a particular direction that isn't necessarily community supported with the same broad user base as a tool like NumPy or even MATLAB?
So it sounds like people are familiar with Yorick, which is interesting. We have one code that still has the sort of higher level layer written in Yorick, but I don't know, for people who are familiar with Yorick, Yorick predates SciPy, right? And actually, Basis predates that, which was another Livermore project. And I think there's a lot of legacy to those projects. So we don't really get that many people doing new starts in things like Yorick. In fact, I think most of the code teams have been trying to move away from that because they've seen the sort of community inertia around SciPy and NumPy and the whole Python ecosystem. I guess, well, I don't know. At least at Livermore, having a community around something is a selling point. And I've actually found it to be easier to get people to adopt things like Spack actually after it's gained external adoption than while it's still just an internal tool, especially for the large production code teams. They don't want to take a lease out on something that they may eventually, they may have to own eventually. They'd rather, build on community software that it knows is going to be there. So I don't know. I think all of those frameworks are very trusted. That they have a future. We are trying to socialize the value of upstreaming. So, if there's something you don't find in a project that you want, I think we've tried to socialize the idea that it's better to upstream support for it than to implement it yourself, because you're going to own it if you implement it yourself, and we'd rather you not, because you have more important things to focus on.
Fantastic. And I think that's going to be a great segue into your prepared remarks. Thank you all for joining us for this game. If you have any ideas for upcoming coding activities, let us know. I hope you enjoyed this, and I'll see you all for the next coding activity next month.
As James mentioned, I think this is a great time to turn things over to Todd. Todd, I hear you have some remarks that you want to share with all of us, and I'm very curious to hear what you have to say.
All right. Yeah. So folks asked me to come here and talk about Spack. I lead the Spack project. I guess I'll just motivate this by, some of the things that people already said. Software reuse. Spack's a package manager for HPC. Why do we need that? Isn't HPC just compiling a single Fortran file and running an executable? No, it's not like that anymore. HPC simulations actually require an increasing number of dependency libraries, as I'm sure folks on this call are familiar with. So, even for a relatively small, single domain piece of software like MFEM, it's a higher order finite element framework. You can get, something with like 31 different packages that you have to integrate together just to build that one package that's probably just a piece of your larger code. Machine learning tools like TensorFlow, LBAN is one of Livermore's ones that sits on top of MPI. PyTorch are, even bigger than that. They're like 71 packages, hundreds of dependency edges. And then, we have large workflows that run on our machines that comprise several different scales of molecular dynamics applications, their own scheduling frameworks for orchestrating workflows, ML training to build models at coarse and fine scales. And those can, run up to like 100 packages or more. And we've got production codes that are even bigger than this. If you look at ECP, the ECP, I think a lot of people think that ECP is a project about deploying exascale machines, but actually the machine deployment was up to the facilities. And so, the exascale project itself, the mission was to build a robust software stack that would run on those machines, so all 3 of the US exascale machines. And that's this thing. It's called E4S, which is the Extreme Scale Scientific Software Stack. E4S is a subset of Spack packages. It's about 100 of them. That's the red ones here. But to build those, you need around 500 other packages just to get the E4S components built. And you can see that E4S is mostly at the top level here, and there's a lot of deeper, low-level dependencies. But I don't think anyone wants to build all this stuff or maintain it or keep it integrated manually. I think it's just infeasible to manage a 1,000-person collaboration with this many software packages without some kind of tool for integrating them all. So this is what Spack's meant to handle, and it targets developers, users, people who deploy software at facilities. We're trying to target the whole gamut of different types of users of HPC. So why do we need something like Spack? If you look at your sort of traditional package manager, there's sort of a one-to-one relationship between your source code and your binary. So like if you look at RPM or tools like it, you take a recipe, you build a binary package out of that, and then you're basically just installing the binary as an end user. And there's this one-to-one relationship between the source and the binary. When you're experimenting for HPC and trying to tune something, you really want to be able to build lots of optimized versions of the code. And so integrating all this software with a traditional package manager it can be pretty difficult because you're likely deploying a portable binary, something that was built for sort of the lowest common denominator. You're not taking advantage of the vector instructions on the machine, maybe not the GPU, things like that. And then a lot of the system package managers assume sort of a common tool chain across the ecosystem. So when you have a $600 million machine where one of the goals is to exploit the max performance on it, you really want to be able to use the vendor compilers that came with the machine because they can likely compile your code a lot faster than the default like GCC toolchain. So Cray compilers, Intel compilers, OneAPI, things like that. And so outside these boundaries with a lot of the traditional package managers, users are on their own. And so traditionally in HPC, code's distributed as source for this reason. People want to optimize it on the machine. You often build lots of different variants of the same package. You're optimizing for the processor and the GPU, and you rely heavily on system packages nonetheless. So you care about the optimized MPI, maybe the optimized math libraries and things that came with the machine. You want to link those in with the things that you're building. And we're sort of plagued with the fact that most HPC software is sort of polyglot. It's implemented in C, C++, Fortran, Python. We see Lua sometimes, and all of those get linked into the same program. So there's these sort of nightmare build scenarios all over the place. And we have to deploy them on 6 different architectures. So people ask, what about containers? Don't they help with this? We're really talking about a complementary tool. So Spack it's a tool for building and for integrating the software that could either go on bare metal or that could go into a container. And containers are a great way to reproduce and distribute a software stack that you already built, but someone needs to build the container. And if you want to maintain a recipe that's portable, that you could build across all those different machines, potentially optimized containers, things like that, You need something more flexible to actually build the containers. So that's what we're targeting. So that's where Spack fits in. It's designed to enable software distribution for HPC. It automates build and installation, and packages are parameterized so that you can easily tweak the configuration if you want to. You can clone Spack. You can run it out of the Git repository. Basically, just clone it from there. You can say Spack install HDF5. That will install HDF5 and all of its dependencies. But we also have a lot of syntax for customizing that installation. So if you want to pick a particular version of something, or if you want to target a particular microarchitecture, or if you want to customize the MPI that you're using, or inject flags into the build, we have options for that. So you can get a lot more control over the way that the software is actually built. We're really targeting the ease of use of the mainstream tools, but with the flexibility needed for HPC. So you can think of this as kind of a telescoping syntax. You could say something as simple as get me this package, or you could be a lot more specific if you want. It's not just an installation tool, it also generates modules. So if you're deploying for users, you want them to be able to say module load package. So we can auto-generate the modules that a lot of sites will write by hand. It has virtual environments. They're a little fancier than maybe the ones in Conda in that you can sort of version them in repos, and you can build a lot of DevOps workflows on top of those environments. Spack it started in 2013. I started writing it because I had a grad student who had about 10 different packages that she had to build repeatedly on the Blue Gene machines at Livermore. And that was sort of maddening because they were complicated. You would upgrade one, it would be ABI incompatible with another. And that sort of repeated for a while before I decided I would try to automate the whole thing. And then, it crept along for a while as sort of an internal Livermore tool until we presented at SC in 2015. And now, we have around 300 different organizations contributing to Spack and over 1,000 contributors to the project worldwide. So this is all the places that we see on the doc site that it's used. And, I don't have a good gauge of how many total users we have for the project, but there's 6,000 monthly active users or so on the documentation site. So it's a pretty large community and a pretty active GitHub repo. So if you want to think about Spack at a high level, there's sort of three components to it. There's the syntax that you type on the command line. And so I sort of showed that already, but you can say Spack install something that's sort of unconstrained, get me a version of this. You can specify a specific version of the thing. You can say what compiler you want it built with. You can expose build options in the packages. You can inject flags, specific targets, and customize dependencies. So you can actually customize any dependency in the graph with this and say, I want to constrain mpitch to be at this version, or swap in OpenMPI for mpitch, things like that. We call this a spec because it specifies what you're installing with the package. And so this is what the user would see if they're just sort of installing things by hand. If you're a packager, you deal with these simple-ish templates. And so these are the build recipes in Spack. They're written in a Python DSL, and you can think of them as having sort of two parts. The whole thing is basically a class. There's a doc string with some metadata. Homepage is where to get this thing. URL is where to download the source. What you'll notice that's maybe different from other systems is there are all of these. There's all the different versions, all the different build options, and different dependency constraints in here as well. And you get basically one of these package.py recipes per package, and it tells you all the ways you could build. So this one, you could pick any of these versions. You could pick any of these options. Then you could pick any MPI you want and any CMake you want to build with it. And so once we pick some configuration out of this space, we go in here to the instance methods, and they basically just tell you how to build. So this one's just saying, okay, this is a CMake package. Here are the CMake arguments that you would pass to the build system. It's just translating these two variants into on and off for CMake. And then this package has no install target because many HPC packages lack some, common nice feature that a modern build system should have. So here we just make a bin directory and copy the executable into it. Most packages don't really need this. You could probably make do with just the CMake args. The build recipes can get pretty complicated. So especially with things like GPUs, I don't know if people have seen the compatibility matrix that every CUDA release ships with. But there's a whole OS support and compiler support matrix. And developers who are sort of getting something to build from source don't really want to deal with all this. I don't know if anyone really wants to deal with all of this. And so you can encode that in Spack into these conflicts and that express basically the compatibility between your compiler and the CUDA version. And that enables us to do some pretty nice things. We can make sort of a mix-in for CUDA packages. If you want to do GPU support, you just subclass this. You get a sort of CUDA on or off option. You can pick a CUDA architecture if you have CUDA enabled. You can, it automatically depends on CUDA, and then we have these rules for, which CUDA version supports which CUDA architectures. This is compute capability, and again, all of those compiler rules. So this is a very simplified version of the package. And we can do this for different GPU runtimes. So like there's a similar support for things like ROCm and the OneAPI packages that I think have a superclass like this as well. And so this is a lot of conditional logic in the packages. So at the core of Spack, between that sort of user specification that says, here's what I want to install, here's all my constraints, and the actual installations, there's this tool called the concretizer, which is essentially dependency resolver if you're used to other package managers, that takes this description, turns it into a graph, basically selects values for all of these different parameters, and gives you something that's buildable that adheres to all the constraints that are coming from the package files. And this is an NP hard problem, as probably the folks who work on things like Conda Forge would know. And so we have spent a lot of time on the solver in Spack, trying to get this very flexible package format to work and to solve fast. We use something called answer set programming for that. I'm not going to get into the details of that here, but essentially, you can have dependencies that map to not just versions, but also all of these different features and flags and options on packages, and we handle that in the solver. Spack allows you to install lots and lots of different versions of the same package. So we do that by essentially considering the whole graph as a configuration. So this libelf node is one configuration of libelf. The libdwarf that depends on it is basically a configuration that is bound to this dependency. We generate a hash for every subgraph here, and each one of these nodes basically gets its own install directory. So we could have MPI leaks built with OpenMPI, MPitch, and BAPitch, and so on. And we could have it built with several different versions of DNinst, all coexisting and able to run together. And we leverage something called RPath heavily for that. For folks who have struggled with LD library path, LD library path is basically a global environment variable that the user sets in their environment to run one thing and screw up all the other things that they want to run. RPath embeds in the executables in the libraries. And so essentially every program that we install with Spack remembers where its dependencies live, so you can just run it. And the rationale for that is that building things is confusing, it's hard. If you do it, you should just be able to run the thing and it should remember the way that it was built. So run the way that you built all the time. You shouldn't have to remember 6 different modules to load to match the build configuration just to run your program. So we try to not require the modules. You can use them to get things into your path, but Spack remembers where the libraries are. So on top of that, we have this environment format. So if you want to work with a lot of different specs together, if you want to install, say, HDF5, libelf, and OpenMPI, you can write a simple spack.yaml file like this with a list of things that you want to install. You can include some configuration or just write some configuration directly in the file to sort of customize how that stack should get installed. And we can concretize this whole thing and generate a lock file with basically the exact build configuration of this stuff. So if you want to reproduce something, you can either hand somebody the spack.yaml file or the lock file. One of these will basically functionally reproduce the stack. So you could build this one on, say, Intel and PowerPC or ARM. And this one, you would basically be reproducing the stack exactly as it was built on a particular platform. We've taken advantage of the fact that we have this sort of unifying YAML format to build some DevOps workflows on top of Spack environments. So if you have a set of packages, you might want to do some things with them, or you might want to use it as a development environment. And so there's things like Spack external find, where we'll automatically go out and try to find things like CMake or MPI or things like that on the HPC system, add them to the environment as things you might want to build against. You can test your environment. You can generate CI pipelines, so like a GitLab pipeline to rebuild all the packages in the environment. And you can turn an environment into a container. So if you want to build a container out of one of these environments, we will generate you a recipe so that you don't have to write the Docker file for it. And then you can also develop packages from within an environment. So if you have something like the environment I showed before, you could say Spack develop HDF5 and it'll get you the source checkout for HDF5. You can modify it and rebuild the whole environment with your changes. If you wanted to say tweak, the way that something was installed. And we're working on fleshing this out as sort of a development environment for some of those larger codes that I showed on the earlier slide. As a project, Spack has a lot of different things. And so, I think the biggest thing is the community, which I showed earlier, that we have a lot of different contributors, a lot of different users who are constantly updating package recipes and keeping them, current. There's the core tool. This is where a lot of my time is spent on developing the core tool and the solver. There's the package recipes, which is where most of the activity on the repo is. And then there's a whole bunch of infrastructure that we use to keep all of that stuff working. And you can think of all of this as a way to build different software stacks and to keep them integrated. So, you saw the ECP stack, which is E4S. Amazon has a stack that they build and allow customers to deploy on their parallel cluster tool. Livermore has its internal stack. There's a math library stack, a viz stack, and every application you could think of as its own software stack with all of its dependencies. It takes a lot to keep this running. So like there's a Kubernetes cluster in the cloud with a GitLab instance, a bunch of runners, both in EC2 and on bare metal at the University of Oregon, so who we collaborate with. And so, a lot of our time is spent collaborating with Kitware to maintain this infrastructure and to keep, several thousand of the packages in Spack building. So we've got CI that operates on all the different pull requests. And that looks like this. We tried really hard to build a CI system that could handle the volume of commits that we get. So, we're getting 400 or 500 pull requests a month that we have to merge. Making sure that the packages continue to build with all that activity is hard, as no doubt the Conda people know. We have this high availability GitLab CI that runs against the GitHub repo, and we have 9 or 10 different stacks that look kind of like this. They're environment files that we build. Essentially, the things that changed for every PR. That gets farmed out to runners in different places, and we get a little check mark on the PR if the builds pass. And for a while, we were just doing this to make sure that the builds kept working. But the users, people get sick of building. It takes a long time, and I think that's one of the things that makes using HPC systems hard is that you have to build everything. So we said, well, do we really need to build source? Could we leverage all these binaries that we're building in the cloud? So we teamed up with Amazon. They're providing a lot of build cycles for Spack, and we are able to provide binary mirrors. And we spent a lot of time on the security of the system. So now basically there's 2 sort of release pathways. You can add a mirror from binaries.spack.io that points to a particular release and get sort of the binaries that are associated with that release. Or we have a rolling release where basically you could get a binary that was built like an hour ago if you wanted to from Cloud CI. We've got something like 3,000 different builds in the cache so far for different operating systems, and we've been trying to flesh that out to include more machine learning tools. And so, you might say, well, if this is operating just on, pull requests, do we really trust those? Because those can come from pretty much anyone on the internet. Security is a big part of, what we try to think about on Spack. We sat down and said, if you're using Spack and you're building from source, what is it exactly that you trust about the project? And we decided that you probably trust the maintainers because if you didn't, then why are you using Spack? So we wanted the source, or we wanted the binaries to be just as trustworthy as the source was, so that people would feel comfortable using them. So what we're actually doing in the cloud is that the contributions come in, and we do a lot of untrusted builds on the raw pull requests that aren't merged into the main line. And essentially, each one of those gets its own sort of build cache in S3. If those work, then the maintainers take a look at the PR and they review the recipe code, the sources and things like that, where the tarball is coming from, not the whole source. And if they like it, they merge it to develop. And once that is done, we rebuild everything from reviewed sources. And so essentially, everything that we put in the develop or the release build caches is reviewed by the maintainers, and we don't pull binaries that were built in this kind of untrusted environment into the public build caches. And we sign these in sort of a separate environment from the build and so on. So the signature basically means maintainers reviewed all of this. So that's what we've got. And so this has enabled us to build lots of different special purpose stacks. So we had the E4S stack building in CI for a while, and the Intel folks came and the Argonne folks came to us and said, well, we want to make sure that all these Spack packages work on Aurora, the Intel system that's getting deployed at Argonne. So we took the E4S stack and swapped in the OneAPI compiler. And essentially, we were able to get that new stack up in a week, building with OneAPI across the stack. There are still build failures because there are some things that OneAPI just doesn't build yet. But the cool thing about this was that we could point the Intel folks to the build errors and basically say, here's all the stuff that we need to work on. So this needs to get fixed in future versions of OneAPI. And so that's, like I said, around 600 total builds for all of E4S. I think we could do this with other vendor compilers. I think we make it a lot easier to think about building an open source ecosystem on top of, say, alternative compilers than other systems. We also put together some machine learning stacks. This took a little bit longer because these things are hard to build. But we've got essentially a CPU, an AMD ROCm, and an NVIDIA CUDA ML stack that includes these packages and some others. Basically the core ML tools that you'd expect. That's 150 line environment files that we're able to use to customize that, and they get tested as new changes come into Spack. So if you think about what we're trying to do, like I said, with the traditional package manager, you'd have these recipes that go into a build farm. You'd build these unoptimized binaries per recipe. With Spack, we're trying to have a smaller set of recipes, basically one per package. People work together on the same recipe. They're sort of forced to think about how their changes to the build recipe would affect all the different architectures it's intended to be deployed on. We throw that in a build farm, and we're trying to leverage testing to enable that to be built in a lot of different places. And so to get optimized stacks out of a smaller set of recipes. And then, we want users to be able to sort of seamlessly integrate source builds with the binaries that we're producing. So that's the idea. 0.19 was released in November, so if you want to check it out, that is on GitHub now. I think that probably the most notable thing for this audience is that this is the last Spack version that's going to support Python 2. We finally ditched it. You'll notice that we are way after the end of life of Python 2, but that's just because things seem to live longer in HPC because Red Hat protracts them for extended periods of time. But we're finally ditching Python 2, and we're kind of excited to start using Python 3 features. And the long-term strategy for Spack is really broad adoption and collaboration. We want to work with a large community, including vendors and other scientific users who want to help us maintain these stacks. I think the growing contributor base is the top priority. We want to keep the effort on the project at a level that can actually sustain all the stuff we're doing. So I think that's it. So if you're interested, check out Spack. It's on GitHub, and we have a Slack instance with around 2,000 people on it. So if you have questions, you can ask away, and we're there all the time.
Fantastic. Thank you so much, Todd. That was an absolutely great presentation you've shared with us. Now I would like to invite our host panelists back on camera. While you were sharing, Todd, we were also joined by Lori Steffi. Lori Steffi was a guest panelist, much like yourself, from March earlier this year, and she joined us along with her colleague Daniel, who were discussing how they scaled Python on large-scale GPU systems and how to manage and promote the use of those systems. So I think we're going to have some great discussion. But I'll just open up the floor. Who would like to ask Todd a question?
Me, I guess. Can I ask the controversial question then and say when the Python community has this tool called Conda that most people know and love. So what are the advantages that Spack could offer over Conda?
So do most people really love Conda? Because that's it. I think I've heard a lot of complaints about Conda and particularly HPC systems. So I think one of the reasons that you would want to use Spack over Conda is because you would want to integrate with things like the system MPI, or build HPC apps that actually leverage the libraries on the system. So if you do, Conda is basically a binary package manager, and there's Conda build, where you're deploying binary packages or you're creating the binary packages. But ultimately, Conda is basically RPM in your home directory, right? You can't build something custom for a particular machine just using Conda, the tool. And so I'd say that's really the main difference between Conda and Spack, is that the package, it's built from the ground up as a source package manager. And the builds in Spack are really just caches of particular source builds. They're not binary recipes the way that Conda has them structured. So I'd say that the integration between the source and the binaries is really the difference.
Maybe I can rephrase the question. Like, how difficult is it to get a package that we have on Conda, because there are so many, into something like Spack?
So I think it's actually, so I would say it's probably easier to write a Spack recipe than to do all the things that are required to make a Conda build. So I mean, I've looked at the Conda builds and there seem to be an awful lot of files involved there, things like ABI pins and stuff like that to actually integrate with Conda Forge. Whereas if you just want to build something in Spack, you can say Spack create and give it a tarball URL, and it'll give you a boilerplate package that you can then just go and write your build code in and build it right there. You don't have to go through either Conda Forge or a custom build tool. So I'd say Conda's really targeted at people who are consuming binaries, whereas what we're targeting sort of developers and people who also just want to build something from source in a new way, not just the way that it's been built before.
So I guess my question is more, once I have the Conda recipe, right? So when I'm a developer and write the recipe file, how difficult it is to go from there to because I guess at some point you have to get, like, what are the requirements of a package and where do I find them in the specific system, right? And like with Conda, it's easy because we only have like one MPI version or like OpenMPI or MPICH, but that's all. I think that your matrix is much more complex, right? So there's a much more complex tree, which versions can be compatible and how to link this. So the question is, like, is there any work on the Spack project to make it easy for somebody who has a Conda recipe to get this built as a Spack package?
So we don't have anything particularly targeted at Conda users. You would have to rewrite it as a Spack package. But I'd say if you already know how to write a Conda recipe, that process is not particularly hard. And I guess the other thing I'll emphasize again is, sure, Conda only has like one MPI, but that may not be the MPI that you need to run on a particular machine, right? So, if I build for MPICH and try to run on, say, Summit, it's not going to work, right? You're going to need a special build for that machine because the system actually uses OpenMPI.
But we have both, right? So we have OpenMPI and MPICH. So the two are there. But obviously not the Cray MPI and the Intel specific one. So that's and then the same is for the CUDA part, right? So the CUDA is still a challenge on the Conda side to get all the different versions in there. But it might be like an easy way to extend the ecosystem to connect to something like Conda to reuse the recipes because they are all available, right? So that's where, like, for me as somebody, like the material science community really had this issue. We looked for package managers. It was very hard to install DFT codes. Most new students are not capable to compile a code themselves, but we might want them to try new codes to just stay on top of things. And so Conda and getting codes into Conda was really a huge push for our community. And obviously we tell them straight up, right? So it's precompiled binaries. You should use them to play around with the code. And when you do your high throughput run, you should either compile it yourself or use something like Spack. But if there would be a way to get these 500 packages from the Conda Forge community and get them easily into Spack, that would definitely be interesting, right? If you now say, I have to write 500 new packages and keep 500 new packages up to date when something changes in the compiling, when plugins change and so on, then I guess I will stay with my packages on Conda Forge, right? So I made a commitment there, and it's not so easy to get somebody like me to then switch with all the packages.
Sure, yeah, I think that's true. I guess I would say it is unlikely that we would try to write something to automatically port Conda recipes to Spack recipes, just because it is very hard to do that. Like the dependency model in the two tools is pretty significantly different, and I think I guess I'm not sure.
Are much smaller, right? So because you only have like a much restricted tree. I guess already now when I compile for OpenMPI and for MPIC, I need different flags depending on which compiler I need, depending on the complexity of the tool, right? So, but having figured out which are the flags for which of the tools, that information is already documented. So if I'm able to convert this and say, okay, as long as you have OpenMPI with a version that the conda specifies, getting the same version in Spark shouldn't be so difficult, right? So I think that.
Yeah, I mean, I think it's actually easier than that. I mean, like, so if you, in Spack, you wouldn't, I mean, the packages are written in a modular way. And so if you don't actually depend on OpenMPI in Spack, you depend on MPI. And it's designed to make it so that you can actually swap one in for the other. So if you want to build against MPIC instead of OpenMPI, you just use the same package. You don't have to, make the packager think about which MPI they happen to be using. We've got some conventions in packages for doing that, and virtual dependencies like that are part of the model. But I'd say in general, like for things like that, for things like CUDA, for sort of high-level interfaces, it is much easier to write a Spack package than it is to to get down to the sort of low-level granularity of like which MPI implementation am I using, like you would have to do for the conda builds. But I'm not sure that exactly answers your question.
But how do you get the information? What kind of flags the program needs? Which part you do? What level of optimization? Let's say maybe MPI is a bit too simple, but let's say I have MKL or I have the OpenBlast library, right? So there's a typical case. If I have an Intel machine, I definitely want the MKL. If I have an AMD machine, I still use the BLAST implementation, the BLAST interface. So I need the flag in my code to figure out where to set these flags. Right, and that's a question, at least on the conda side, that's still manual work of the maintainers of the recipe to figure out which are the specific flags for one package to compile with a specific library.
Sure. So I mean, if you are looking for, I think the difference is really that in Spack that kind of combinatorial stuff is pushed into the person who packaged, say, MKL or BLAS. So like if I look at the dependence on BLAS, right, this is a virtual interface in Spack. Any of these could use, say, MKL or OpenBLAS or whatever, right? And the package itself doesn't actually specify the flags. You can ask the BLAS provider, so you can ask OpenMPI, you can ask OpenBLAS or MKL what libraries or what flags you need to use for your particular build. So it's sort of inverted from the way that the conda recipes are written. So for example, like if I edit hyper, right, here's the hyper recipe, here's all the versions, here's the BLAS dependency.
A moment.
Oh, do you see my screen still or no? Is this better? Yeah, so if I ask Spack, what are the dependents of BLAS? It's going to tell me all the packages that depend on BLAS. And any of these could use MKL or OpenBLAS or the netlib implementation. And if I edit, say, the package that depends on that.
But then the internal interface that you link to is the BLAS interface. You don't link to MKL routines in particular.
You can depend directly on MKL if you want to, but you can also depend on BLAS and just use MKL as the provider. Right?
Yeah, sure. But that's a simple case, right? So what I typically have when I look at a density function theory code, like a simulation code for optimistic simulations, they are optimized to directly bind to MKL, but then I use different flags, or I can use the BLAS interface, but then I lose a bit of performance on the specific hardware. Right?
Yeah.
So, and then I want these two versions to be available. And that's the main work that I put on the conda side is just to figure out, okay, what are the flags to link to MKL? What are the flags to link to BLAS? Because that's, unfortunately, with the DFT codes, every DFT code needs different flags, right? So that's, I guess you showed the CP2K. That's one of the codes that we have in there. Unfortunately, each of them have like different parts to how we link to the different codes.
So you can look. So in the package here, you can see that they're basically asking whether they're depending on different implementations of BLAS or the FFT interface, right? So this is basically the special case for the MKL code, if they want to special case it, and so on. So yeah, you can ask if you depend on a virtual like that. You can say, hey, which implementation did I actually get, and do something special for that if you need to. But in the simple case, you would basically just say, hey, like depends on BLAS. and you wouldn't have to think too much about that. And you can see that they've got the optimization flags in here embedded for different compilers if they want to be real specific about which way they build on which compiler defines for FFTW and so on. But in general, it's pretty concise, right? And it's one recipe for all the different compilers.
But it's 300 lines. Right? So I guess the conda recipe for CP2K is much shorter.
So this is like 788 lines for the CP2K recipe. Sure.
Okay.
Yeah, so I haven't looked at the specific recipe in conda for CP2K.
So I guess the two things that we make is we only build the latest version, right? So we don't support the other versions, and then we only support a much smaller subset of different codes, right? So we only have the standard compiler, we have the two different MKL versions. So that's why I think, right? So from my perspective, it should be easy to build a tool to migrate packages from CondaForge to Spack because it's a much smaller stack. But I guess currently I'm missing the expertise, right? So and I won't take the effort to migrate 500 packages on my own, right? So it's but I could see that there may be more like I at least know here in Los Alamos we have other people from other communities. So for the climate science, for example, who also have a whole stack on CondaForge, who have the same troubles of going when they go to the big machines, they still have to compile on their own. So there is the community is there who wants this kind of features, but I guess it would be great if there would be an easy way or at least some tutorials. What's a simple way to go from CondaForge recipes to something like a Spack recipe?
Yeah, I mean, if you have people who are interested in that, I think it would be awesome to get them together and to try to write some general rules for like porting, say, from CondaForge to Spack.
Yeah,
I think it'll be a little bit manual, but yeah, I think that could be great to get the two communities together.
I'd actually be curious if the other way is possible to use Spack to generate CondaForge compliant tarballs.
So we basically generate relocatable binaries. We have different rules around relocation than Conda does. And so I am not sure that we would be doing everything to spec for what Conda requires, because I think we're a little more aggressive about what things we're willing to relocate. So like we'll dig into binaries and relocate strings and things like that. We don't raise all the same flags that like the Conda's relocation detector tool does. And I think we allow a broader range of binaries to be relocated. So I don't know. It's not outside the realm of possibility, though. I mean, like I think you could definitely take a Spack tarball and send it over to CondaForge and have it untarred in a particular location.
Great. Well, this has been. Oh, yeah, Tom.
I dumped a link to a discussion on Python where the Conda and pip people were having this exact discussion about why Conda and pip don't, or Conda and wheels don't get along particularly well. Basically, his wheels vendors everything into themselves, and Conda vendors nothing, and so now mixing and matching is extremely hard.
Well, I mean, I guess the other thing is the installation model, I think, is different between Conda and Spack. So, I mean, in Conda, you're assuming a single prefix environment where you've dumped all your libraries, and they basically assume that their dependencies are going to come from there. I think you're leveraging LD library path pretty heavily within Conda to load things just from the environment. Whereas in Spack, it's more like, I don't know if you're familiar with Nix, but the deployment is basically everything gets its own prefix. And so the R paths in the binaries are actually pointing out to all the different hash prefixes from the dependencies. So it is designed pretty significantly differently from the way that Conda is. So there's I think there'll be a lot of ABI nastiness in trying to make that happen.
Definitely. Well, it sounds like a fantastic solution here that you have in what seems like an extremely complex problem. I did want to take a note of the time and just ask if any of our host panelists had any final comments or questions before we wrap up for the day. All right, and if not, I did want to note before we adjourn, we will not be having an exchange next month in December. However, in January, we will be joined by Pablo Galindo Salgado, who you may know is a member of the Python Steering Council and is a C Python core developer. His most recent work revolves around implementing the better error messages that you've seen starting in Python 3.10 and continuing his work more recently. But what you may not know about Pablo is that he's also a theoretical physicist specializing in general relativity and black hole physics. I want to send out a huge thank you to our guest panelist, Todd, today, as well as each of our host panelists and all the attendees who have joined us for this exchange. And I'm looking very much forward to seeing you all of our attendees and host panelists again next time in January. Thanks, everyone.